So I'm excited to learn about that, and please take it away.
It's fine, everyone. I just like monitors the.
The microphone's just for the stream.
So hello, everyone. Welcome to my Cirrus, and I'm like very excited to talk to everyone about it. So. All right, so let us begin. So, a little bit about myself first. I'm currently in third year studying like astronomy and physics here at the University of Toronto. And my research interests are mostly astroparticle physics, and I'm also currently interested in how the evolution of galaxies works. My favorite particle, it is compulsory to mention this in the physics stream, is like the gluon. And I do like to hike and travel in my free time. So, all right. So for this talk, I've decided what we are going to start with is we can start with the background of the ISM, and then we move on to a discussion about what the Galactic Cirrus is, what motivated the problem that we're going to tackle, and what my research yielded. Um, all right. So to begin with, this is a term that is going to show up quite often. It is the ISM, which is the interstellar medium. And the ISM just represents the medium that's present between the different stars in our galaxy. Not just in our galaxy, but also like other galaxies. So combining this, it's kind of it includes both the matter and the radiation between the stars. It consists of dust, consists of our gas particles. It also consists of radiation, which are like the photons that are free floating in the galaxy. Now, one thing about ISM is that its density is extremely low, especially in the regions that we are going to study it for the purposes of this talk. The density is around 1 particle per cubic centimeter. However, this is actually very crucial for our star formation, for the chemistry of the galaxies, and how light actually propagates throughout this medium. In our galaxy, we can see that the composition of the ISM is actually not that diverse. Around 99% of it is just the hydrogen and helium gas. I would mention here that the gas is ionized, and 1% is like other silicate components. And this is the thing that obstructs our view to the central bulge of the galaxy. So some common components of the ISM here, I have tried to recreate them. So just visually on the left-hand side is our galaxy when viewed through visual telescopes. But on the right-hand side, we can see the different components of the galaxy. This one is in the infrared image. Just because you will notice later on that when we are looking at our galaxy, infrared light seems to work the best. Because of all the dust particles that are present there, you will notice that actually the difference between the dust particles is like so small that any light wavelength that is smaller than the distance between the two dust particles cannot reach us here. All right. So let me talk about the Galactic Cirrus. So the Galactic Cirrus is just these wisps of filamentary clouds that you see on screen over there. This is just a projection of the dust and gas that we are seeing, the interstellar material that we are seeing. The kind of like the central main line is just the central bulge of our galaxy, but we're going to talk about ISM that's like spread throughout. I'm going to focus on high latitude ISM where the density is actually really, really low. So we're going to focus on like these upper regions of the galaxy, right? They were first discovered in 1980s with our very first infrared telescopes, the IRAS missions and the Planck mission. Here it's just seen in the far infrared, and I've written down like the wavelength of light that's associated here. So let me talk a little bit more about what the Cirrus actually contains. So the Galactic Cirrus is, like I said, filamentary in nature. It's called the cirrus because if you're in atmospheric physics, you might have encountered the term cirrus clouds. And these clouds are just like really, really thin clouds that are shaped into filaments and just stretched really far. So one thing we'll notice that in our galaxy, the cirrus is highly elongated. It follows kind of the shape of the galaxy, right? And the filaments are really big in size. They can span parsecs. They can span millions of light years. Some of the common features that we're going to see is that they do have like a fractal nature that on small scales when viewed, it actually really hard for us to make a distinction if we are viewing it on like a larger scale or like a smaller scale. What about like the physics that kind of shapes this? It's still an ongoing field of research. Right now, we think it might just be the MHD turbulence, which is magnetohydroturbulence. So essentially, we're saying that the magnetic fields shape the filament. It could also be the dust gas coupling, that is the collision between the dust particles that is shaping it. Or really, it could be anything. The reason is not yet clear. I will like to mention that it could be that it's not just that these magnetic fields shape the cirrus, it is also that, you know, the existence of cirrus and the underlying structure could face the magnetic fields, could make the magnetic fields that we observe here. Um, One thing I forgot to mention before, but let me talk a little bit about the scale at which we're going to discuss things. So the ISM, like I said, spans parsecs, right? Could span millions of light years. And at those large scales, it's really hard to distinguish like really anything. So what we like to do is we like to study it on a smaller scale. And the scales I'm talking about here are the scales of like particle physics, right? At those scales, the state of ISM is just like a gaseous state. So really we can apply all of the dynamics, all of the kinetics that we've learned about gaseous molecules. So one of the objectives that we're going to discuss here is the turbulence inside galactic cirrus. Like I mentioned before, it consists of dust and dirt particles that are constantly colliding with each other. So we expect there's going to be some sort of chaotic nature associated with it. And kind of the chaotic nature that I refer to here will be the turbulence. And what I'm specifically interested in knowing is if it follows like a Kolmogorov energy scaling. So kind of before I get into what that exactly means, let me discuss a little bit about why it's this important for us. So understanding the structure of the ISM, I would say, is really, really important, right? Because these filaments, like I said, provide a basic structure, and that structure determines the areas where we could see potential stars that form, or any sort of astrophysical object, really. Um, you know, dust present in the ISM traces the gas is turbulent, and so, you know, the cirrus explains like the chaotic movement of stars that follow this structure. So, like I said, it also actually is noticeable in the CMB measurements that are conducted. CMB is the cosmic microwave background radiation. Whenever we point our radio telescopes up, we can measure the CMB. So that is just like out there. Right. So let's get into how we would go about determining the structure. Like I said, this is still a developing field of physics. There is really uh, no such like thing where we've actually mapped out the entirety of our galactic cirrus, but there are certain portions that have been mapped out. So in this project, I kind of used the um, maps obtained from the IRAS and the Planck missions that I mentioned before. We're going to use the uh, infrared data measurements that we made, right? So the IRAS mission is really just the very first infrared survey that was done for the entire sky that data really, really important. And that was when it revealed to us that, oh, there are these clouds that actually shape the structure in our galaxy. It revealed to us the existence of the cirrus. Like I mentioned before, we are going to focus in the high galactic latitude. What that means is that when observed here from the Earth, uh, essentially we're going to focus in the regions where we are currently. So Canada is like a high latitude. The ISM here is more diffuse. The density is not that, it's even lower than what I mentioned before. And the emission here is actually dominated by the cirrus dust emission. So what that means is that excludes the emission that we would expect to get from like the central bulge of the galaxy. So think back to the picture I showed earlier and just subtract off the really bright central portion. Right. Um, I have included kind of the website name here for people interested in knowing where the data was obtained from. It is in the HILPX format. Really, what that means is, so, when we're observing things, how do we get like a 2D projection of the data? And one of the techniques that was used is that, we're observing it all over the globe. Essentially, to project it here, what we do is we convert like the equal area, equal pixel ratios. Dividing areas, like assigning them to every single pixel, we get kind of this elongated picture. Here is like a really common example that people might recognize. This is the cosmic microwave background. So we're going to focus on the 857 gigahertz range. Uh, this is far infrared. Essentially, what we're trying to do here is focusing our studies on wavelengths that are constricted to 350 micrometers. It's really large, but this is the wavelength that actually gives us the best estimate for the ISM that we observe here. Like I mentioned, it is very diffuse. The density is not that high, so we need like the higher range frequency. So here I kind of just visualize the areas. It's not visible at all. But we are going to focus on latitudes kind of like from here up to like these areas of the sky. And what I did over here is, so this is like a 10-degree by 10-degree image of the sky observed in that little patch over there. And this is an ultra magnified sort of image here. So the galactic filaments that I'm talking about, when we kind of like zoom in to the galactic cirrus, we're going to observe that we sort of have these filament shapes like here, or the bulges that you can see like right here. And in the central of these, we have objects that are obscured by these filaments. But the focus kind of is when we talk about like the galactic cirrus is just like the structure overall. Why is it sort of filament shaped? Is like the end goal for study of this. So kind of like a close-up of the data. These are ISM bulges uh, in the sense that when we're receiving data, we like to isolate certain like portions where it is the most concentrated. The red and the yellow dots just have different sort of compact objects. They could be stars here, or could be neutron stars. Really. So any sort of astrophysical object is like determined here, and the sort of like these gray bulges that you see is just the uh, dirt and the dust that is obscuring that. Uh, this image was not influenced by me. I just like picked it because I thought this was a good representation of the problem that kind of we're struggling with here. Uh, right. And then, well, this is more data, which you do not have to concern yourselves with. But so I will use this in my like further slides, but this is something I just wanted to showcase. So right. So I so now getting back to the question of determining like the energy cascade. So what exactly is the energy cascade? if you notice, I was talking about like observing ISM on different scales. We could talk about it when you're just viewing it from outside of the galaxy, like on the galactic scale. On the galactic scale, it really is very uniform. You can't really tell those bulges that I was showing you earlier. So we kind of like, starting from the talk of those scales, let us try to now zoom in to the actual like bulge area. The energy cascade, what that means is just how does the energy flow from like the when viewing it from the bigger scale versus how does it flow when we're at the smaller scale. So what is the energy flowing like when observed from really far away versus what it is close up, right? And when we analyze kind of this material here, uh, I kind of hypothesized that maybe it flows like a Kolmogorov flow in the sense that this is actually a very common, well-known sort of flow for gaseous structures here on Earth, right? This is how high energy gas tends to flow here. So I was like, let us model this data that sort. What I have here is the power spectrum plotted on the left-hand side, right? And the power spectrum was obtained from the data I showed you earlier. I just performed like a Fourier analysis on it to get the power series here. And then I was like, okay, well, on Earth here, for really turbulent gas structures, what we get is something of the form energy is going to flow something proportional to, some variable to the power negative 3, negative 5 over 3, right? And so I kind of like just took the log of both sides to make the plotting a little bit bearable. And I obtained the following like power structure series, right? And then we observed that kind of like this was my slope measurement here. I got like a slope of 2.9, which is actually really close to like negative 5 over 3. No, not really, it's not that close. But that is also a good result in the sense that since it's a little higher than what I would expect, right? And the reason for that is because in this research, I have not included the magnetic field distribution inside. I only model like the specific data, right? And the magnetic fields actually form a significant portion of the galactic cirrus. They they make the spectrum way more steep than what I expect. So expanding on that, kind of like, what I found that the energy cascade was not really Kolmogorov. It certainly has to be MHD, right? We have to include the sort of magnetic uh, contributions that I did not include in this data, right? But now what we can be sure about is that distribution is indeed like it follows the MHD turbulence growth. The dust grains have to align with the local magnetic fields, so the emission is polarized, right? And what that does is, if we think back to the original image I showed you of the CMB, it can actually explain why we have anisotropy over there, right? So anisotropy is just saying that why do I get those regions and why are they different colored? Why is not all pixels? Why are they all the pixels not just the same, right? This slope is closer to this, right? Like I said before, not really Kolmogorov. So it doesn't actually follow the same patterns of turbulent gas flow that we know here, right? Some deviations that people here might be interested in is that so now we know that the dust is coagulated in, let's say, this portion of the galaxy. What does that tell us? Well, if it's like a significant amount of these coagulates, that could directly collapse to stellar formation. So we could expect that maybe it's like a protostar there, right? Also tells us about the changes in local radiation. Now, the reason why we can't actually determine if it's like an MHD turbulence is like I told before, that it's like a developing field, right? So modeling the magnetic interaction of the entire galaxy is really, really hard. So it's not been done yet, but it's in progress. kind of like going over some further goals or like just the discussion of this is like, well, dense star forming clumps first appear in diffuse filaments. Like I showed you before, we have those clumps there. Those dense clumps are eventually, maybe over time, going to collapse into future stars. So the distribution in the structure of the ISM actually tells you where we could find potential stars. It also tells us about local stellar populations, right? If you follow those filaments, in the bulges of those filaments, you're often going to find really compact objects, right? So these so the turbulence in those fields are also going to be an indicator of the movement of these stars there. Like I said, prestellar cores form stars. An extension to this, it is an ongoing field of study. We still need to characterize sort of all the types of observed compact objects. Magnetic distribution is still not clear. So kind of like knowing or determining what the actual flow of the turbulence is really, really hard in any case. So for now, what scientists are focusing on is kind of like, let us just try to see, like I've showcased before, we're just going to analyze it in small patches, and maybe we could add up those contributions to see what the entire turbulent flow of the Cirrus is like. I went over it a little fast. Are there any questions for now? Yes. Um, that actually really depends case to case, just because, we are actually only eliminating the dust in the foreground. So the light coming from the background object is really only telling us, okay, maybe this is the region that's obscured by the dust and gas, right? So to determine how far away that object is, though, is a challenge. And it's actually we do have a way to remove those background signals. It was actually included in my report. I kind of used the reduced Planck data set that kind of accounted for those and already had those signals removed. Yeah. Oh, yeah. That was like it. I realized it was 6. Yeah, if there are more questions. It is quite big, and that is a very good question. So when we're talking about ISM in general, it consists of different media. That is, so in here, I kind of just use ISM as like the stellar media of the entire galaxy. That's a different scale. But when we talk about planetary formation or like stellar formation, the scales I would talk about is like about a few AU. That would be comparable to our solar system scales. But when we talk about the structure of the actual filaments, they are quite a few light years. Compared to like our galaxy, I would say they're comparable to the galactic scale itself. Does that answer your question? Yeah. Yes. Yes. Uh, that's a really good question. Again, it's like it's an ongoing field of research. But so the turbulence over here that we're talking about is kind of the relationship is not really clear. It's kind of the question where you're like, maybe the filaments formed first and then all the compact objects followed that structure and are in the places that we see them to be. But on the flip side, it could also be that the structures formed first, and then they kind of influence the filaments to shape the way that they are. The source of the turbulence really is because the galaxy is a very active place. You're having stars that are born, stars that die, and we could have supernova explosions. The shock waves just like they're always present in the galaxy. That would be the main source of turbulence for now. But it could really be any like sort of stellar wind it's like nearby. Yeah. Thank you. That's a really good question. In this case, total magnetic field of the galaxy is like really, really hard to model. You have to include the contribution of sort of every single particle that's in the galaxy, and that is not as of right now. When we talk about magnetic contributions currently, when even scientists talk about these well energy cascades, we actually can't model them beyond a local stellar population. So like we're talking about maybe the scales of like star clusters. Again, it could just be like it's comparable to the scales of our solar system. That is to the extent we can map the magnetic field over the entire galaxy. The ISM itself is ionized. So like each of those dust particles, when they collide with each other, they're producing uh, just because they're ionized, they're going to have a magnetic field. So when we talk about the overall magnetic field of the galaxy, we will have to add in the contributions of all of the ISM particles. It is a very hard task to do. Right? Question. Right, right, right. So ISM really can be anything between the stars in our galaxy. So like anything except for the empty space. And when I talked about the composition of the ISM, that's talking about in general what are the components that the ISM is made of. Now, the most common components are hydrogen and helium. So they actually form the most of like the elemental composition of the ISM. Now, the state in which they are present is quite different. There is such a thing as like warm ISM versus cold ISM, where we talk about kind of the temperatures to which it is heated. Um, so it can vary from like different corners of the galaxy. It is not a fixed sort of distribution. Yeah, and also like adding on to that, we could have hydrogen, helium. Mostly, we talk about molecular hydrogen. It's just like saying it's ionized gas. Yeah, good question. Are there any other questions?